In our last video, we learned how to define what drag is, and we also learned about a simple model, which we've got shown here in the upper right-hand corner. So in this model, we can look at the shape of an object, the density of the material it's moving through, which we're going to assume is air, the cross-section of the object, and the speed of the object. And from that, approximate the drag force that the object is experiencing. Now remember, this drag force always points in the direction opposite of the motion of the object. So we also said that because this drag force depends on speed, the drag force often is a variable force, not a constant force. So in what instances could we possibly have where we might have a constant drag force? In order to do that, we would need a zero acceleration. So if our acceleration was 0, then that means the change in velocity with respect to time is also going to be 0. So that's telling us that we have constant velocity. Now, if acceleration is 0, then that also is telling me that my net force over mass has to also be 0. And since we're dealing with an object, that object has to have mass, that's really telling me that my net force happens to be 0. So, in order to have a constant drag, we have to have an object that is moving with a constant velocity, which is telling me that my net force has to be 0. So my forces have to be balanced. My object is in equilibrium. So if we have an object that's falling, this particular situation that results in 0 acceleration will only occur when I've hit what we call terminal speed, sometimes also known as terminal velocity. Otherwise, if it's moving horizontally, it results in a maximum speed. So let's take a look at what each of these two possibilities will give us. In the first case, when the object is falling, it needs to fall far enough in order to be able to reach terminal speed. So not all objects will do this if they're falling a short distance. But if it gets to the point where it does reach terminal speed, then as we said before, the acceleration is 0, which means our net force is also going to be 0. If we consider breaking that into components, that means that if we add up all of the forces in the x direction, those would be 0, as well as all of the forces in the y direction. Now in this particular example, the only forces on our falling object are the force of gravity and the drag force. So these are both forces in the y direction. So I can go ahead and take the sum of my forces in the y direction and set them equal to 0. Which means that my drag force must be equal to my gravitational force, which is equal to mg. So if I plug in now for my drag force, I can maneuver this equation around, multiply both sides by 2, divide both sides by c, divide by both by rho, divide both by a, and find that my velocity is going to be equal to the square root of 2mg over rho, c, and a. So this is known as the terminal speed. So when an object reaches this speed, based on its own mass, our free fall acceleration g, the drag coefficient that corresponds to that object, rho, the density of the air at that location that the object's in, and a, the cross-section of that object, it will reach that terminal velocity, and if acceleration is 0, it will not speed up anymore. And in fact, the interesting thing is, if an object initially starts with a velocity higher than that terminal velocity, it will actually slow down until it reaches this point. So terminal velocity works both for objects that are speeding up towards the terminal velocity, as well as objects that need to slow down to get to that terminal velocity. Now, if we're looking at the horizontal direction, then this is going to give us what we call maximum speed. But the idea is essentially the same. So we've got an airplane here. The engines on this airplane are giving it some sort of thrust. Drag is going to be pulling against it. And so just like in our previous example, we've got two forces. If we get to the point where acceleration is zero, then these two forces must be equal to each other. So you could go through and calculate the maximum velocity by doing the exact same calculation we did before. And it would just be based on whatever that possible maximum thrust force happened to be. So now that we've talked about terminal velocity, otherwise known as terminal speed, and the drag force in general, take a minute to think about this question and try and answer for yourself in the Play Pause It video. Which of these 5 options do you think is correct before we go through and work the problem ourselves? The terminal speed of a styrofoam ball is 15 meters per second. Suppose a styrofoam ball is shot straight down from a high tower with an initial speed of 30 meters per second. Which velocity graph is correct? So take a moment, think about it, and we'll answer the question together afterwards. All right, let's start out by identifying our knowns in this problem. We've been given the terminal speed as 15 meters per second and the initial speed of 30 meters per second. So in this example, my object is starting with a faster speed than terminal velocity. So that's telling me that my object is going to slow down as time goes on. Now, because this object is being shot straight downwards, we normally pick up to be positive. So I would expect my speeds here, if I were to include positive and negatives to correspond to directions, I would say that they would be negative speeds because they are moving downwards. So this would actually be a negative 15 and a negative 30. And if we look at the graphs, we can see that all 5 graphs show negative speeds. So that's a good place to start. Next, we know that it's going to start with an initial speed of 30, which we can see all 5 options do. But we also can assume that this is going to be a high enough tower that our styrofoam ball will reach terminal speed, which is negative 15 meters per second. So graphs A and graphs E do not stop or even reach that negative 15 meters per second. So I know that it can't be those options. So I'm left with B, C, and D. We can see that B and C both have linear slopes to them for at least some section, whereas D looks like a curved graph. So let's go through and talk about what's going on before the styrofoam ball reaches terminal speed. Before it reaches terminal speed, our acceleration is not going to be 0. We will have an acceleration. And that is going to be because our drag force is going to be greater than the force due to gravity at that point. So we're going to have an acceleration, and because of because our object started with a higher speed than terminal speed, that acceleration is actually going to oppose the motion and slow it down. Now, if I go through and think about what each of these forces happen to be, I can plug in for my drag force. I'm going to drop the vector signs now because these are all in the vertical y direction. And I'm going to call all of this stuff just alpha. So I can say alpha squared minus mg equals ma. Because I wasn't given the numbers in this problem and I know all of that is a constant, The drag coefficient is not going to change while the styrofoam ball is moving through the air. The density of air is not going to change while the styrofoam ball is moving through air. Neither is its cross-sectional area. So all of that is a constant that I may not know right now, but it is a constant, so I can call it basically whatever I want. So if I go through and look at this, I also know that mg is a constant and is not going to change. So because my speed is going to be changing, and this is its instantaneous velocity at any point in time, then that means my acceleration is going to be constantly changing as well. So in order to go through and solve this equation, I actually need to know how to solve differential equations, which is a higher order math that you all have probably, in most cases, not gotten to yet. So we're not going to solve this mathematically, but we can still go through and get an idea of what's going on to be able to pick the correct graph. So, in order to go through and think about this, we should focus on how the velocity is changing in each of these graphs. So in in graph B, we know that the acceleration is the slope of a velocity versus time graph. So if I look at the slope here, I can see that this slope is somewhat steep, but the slope itself isn't changing. So that means A is constant. Same goes for the acceleration in graph C. This is a more gentle slope, so that number will be lower, so this would be a smaller acceleration than what's going on in that section of graph B, but it's still just a line. So I could do my rise over run, I could do my calculation, and I could find out what that acceleration is, and it would still be a constant acceleration because the slope is not changing with respect to time. But if I look at D, I can see that the slope starts out very steep and then starts to level out as time goes on, eventually getting really close to zero. So in graph D, the acceleration is changing over time. Starting out with a high acceleration, and then moving to a low acceleration, and eventually a zero acceleration as it reaches that terminal velocity. So, based on this, the answer to the question is D. That not only is the speed going to be changing, but the acceleration is going to be changing until the object reaches terminal speed.